Okay, so the quotient rule is the last one that we're going to be doing. So this one's very, very similar to the product rule, as in that the way we're going to design it is going to be similar, but there is a subtle difference with this one and the product rule. So let's suppose we have, we'll suppose we have a function y is equal to something to do with x over something else. So we've actually technically dealt with something similar to this, but we're referring to when the bottom of our function is something that's not just a single value of x. So e.g., we might be saying that we will have y is equal to, I don't know, x plus 5 over x squared plus 2x, something like this. Now that's quite we don't know how to differentiate that yet. Okay, and this is the topic where we're going to be looking at it. So in this case, we're going to be calling this our top, our u, and our bottom, our v. So the quotient rule says that if y is equal to, u over v, then dy dx is equal to. Now, it's a fraction, and it's going to be similar to the one that we did before. We're going to start with v du dx, and then we're going to go minus u dv dx, okay? And this is all going to be over v squared. Very different to what we have been used to, and you can prove it by using the chain rule. Okay, so we won't worry about that. If you're concerned about that, you can have a look at your text, but you can use the chain rule to prove that that's the case. Okay, so dy over dx is equal to v du dx minus u dv dx over v squared. Okay, remembering that the u and the v is just the top and the bottoms of that fraction. So let's jump in and have a look at an example. Differentiate each function stating any values of x where the derivative is 0. So once we've done our differentiation, we need to then work out, well, when is the derivative equal to 0? Okay, so in other words, we're trying to find where the tangents are horizontal. So we've got y is equal to 2x minus 3 over 2x plus 3. So what I'm going to do is I'm going to say, well, let's let this be equal to u and this be equal to v, okay? So let u be equal to 2x minus 3. So that's going to make du dx, okay? So derivative of u with respect to x is going to be equal to 2. And alternatively, we're going to have v is equal to 2x plus 3, which makes it very convenient for us. So dv dx, in this case, is also going to be equal to 2. So if y is equal to 2x minus 3 over 2x plus 3, then our derivative dy dx is equal to v lots of du dx minus u lots of dv dx over v squared. Okay, so you might remember the v squared. If we bring it up to the top of the fraction, it's v to the minus 2. Or originally v to the minus 1 comes up, and then it's going to be an application of the product rule in that way. But let's continue on. So let's substitute our values in. So our v value and our du dx. So we'll put in du dx first, which is 2. So we're going to get 2 lots of 2x plus 3. And we're going to subtract 2 lots of 2x minus 3. Okay, and that's all going to be over v squared. So v squared in this case is 2x plus 3 all squared. Okay, just like that. Okay, so sometimes you might be asked to expand it out and leave it as a fraction. Some other times you might be asked to find zeros. If you're asked to find zeros, leave it in the fully factorized form. It's going to make it a lot easier in the long run. So expanding this out, we're going to get, okay, so 2 times 2 is equal to, or 2 times 2x is equal to 4x plus 6 minus 4x plus 6 again. And that's going to be all over 2x plus 3 all squared. So, continuing on, we're going to now put in some, well, we're going to simplify this. So the 4x and the minus 4x, so this one and this one are going to cancel out. And we're going to be left with 6 plus 6, which is equal to 12. 12 over 2x plus 3 all squared. Okay, so our dy dx, so our derivative is equal to that. Now, the rest of the question says, well, when is this function equal to 0? Well, this function's never actually equal to 0. Because for this fraction to be equal to 0, the top is always positive, the bottom needs to be, well, sorry, let me rephrase this. For this thing to be equal to 0, the top of our fraction needs to be equal to 0. But the top can never equal 0 because it's always a positive whole number. So therefore, what we're going to say is that there are no zeros in this function, okay? So because the top can never be equal to 0, there's going to be no zeros in this function whatsoever. So whenever we graph this function, there's going to actually be no point on the function where the line or the tangent that it makes with the curve is going to be flat. So that's part A. Let's do part B, which is a very similar one. Similar, but again different. So we're going to start off by doing let u be equal to x cubed. So it means that du dx is equal to 3x squared. And we're going to let v be equal to x squared plus 4. So dv over dx is equal to 2x. Okay, so if y is equal to x cubed on x squared plus 4, then dy dx is equal to v du dx minus u dv dx. Okay, so they're the opposites of each other over v squared. Okay, so let's substitute the values in. So our v and our du dx. So du dx is equal to 3x squared, lots of v, which is x squared plus 4, minus u, which is x cubed, lots of dv dx, which is 2x, and that's all going to be over v squared. In this case is x squared plus 4. So x squared plus 4. And that's going to be all squared. Because it's v squared, so it's whatever v was. So back up here, our v is x squared plus 4, and we're just going to square that. Okay, so expanding this out, we're going to get 3x to the power of 4 plus 12x squared minus 2x to the power of 4 all over, and I'm going to leave this one as as in its factorized form. Okay, but I'm mainly doing this so I can do some cancelling on the top. So at 3x to the power of 4 plus 12x squared minus 2x to the power of 4, so 3x4 minus 2x4 is just x to the power of 4 plus 12x squared over x squared plus 4 all squared. Okay, so that is what dy, oh well, we can go one step further, I should say. So dy dx is equal to, so x squared comes out, and we're left with x squared plus 12 over x squared plus 4 all squared, like that. Okay, so that's the derivative at that value. Now remember, dy dx is equal to 0 when the top is equal to 0. So when x squared, lots of x squared plus 12 is equal to 0. So that is, and I should go over x squared plus 4 lots of 2. Okay, and so that is when x squared is equal to 0, or x squared plus 12 is equal to 0. Okay, so when is this thing equal to 0? Well, x squared is equal to 0, so x must be equal to 0. However, if we have a look at the other side, the x squared plus 12 is equal to 0, well, there's actually no solutions to that. Because there's, if I take the 12 across the other side, it's going to give me a negative 12. And so it turns out that the only horizontal for this one, okay, so this one doesn't actually exist. The only horizontal for this one is when x is equal to 0, okay? So, with that being said, that's the end of this video. Okay, it's the end of this video. And it's going to finish off this week's lot of learning. So we only got a few lessons left of our differentiation, and then we're going to jump into our next topic of our next extension 1 topic, which will be our polynomials. Okay, so we've got a little bit left of differentiation, then we're going to jump into polynomials, and then we're going to come back and then do some more differentiation once these rules have having a chance for these rules to sink in. Okay, so with that being said, that's the end of this video, and that's the end of this week. So I'll talk to you guys in the next one.